Okay, so let's continue. So we had some slides from last lecture about where we talked about C. So we want to wrap up that first. And then we will continue on with real-time operating systems. So we will introduce it today, and then on Monday next week we will talk about how to actually program using C on a real-time operating system, the free RTOS that you have on the Crazy Fly. So which will be then done in, this is something you will do then in the next hand-in after the ethics essay. By the way, so the ethics essay is now, there are 3 different cases that you will dive into, and I did update one of the use cases because it was the same that Carl presented here. So, but there are now, everything is done now, so you can start to work on those if you like. Okay, so this is where we ended last time. We talked about arrays, and especially we talked about how you can iterate over an array. This is something you need to do later on when you do implement your control algorithms. So for example, if the control signal is a linear combination of the states, so every state will be multiplied by a constant, and the states are stored typically in an array, right? So you iterate over the array and multiply by constants. So the important thing to remember when you program in C is that arrays, the first element in array you find at slot 0. So you can find the elements from 0 to then the number of elements minus 1. And the way to do it is to iterate like this. So you have initialize some counter here, and then as long as this condition is fulfilled, you will do what's here, and then when you're done, you will increase I by 1. Yeah, something else that is worth remembering is that there is no string type in C. So strings are just a sequence of characters. So you could, for example, if you would like to encode a string, you can have it like this. So it's an array of character elements. Yeah, so what is worth to remember as well is that if you declare an array like this, then there will be memory allocated for that array on the stack. So if this is in a function, it will be put on the stack. So in this case, you will have 5 characters then. So you will get space for that on the stack for all these 5 elements. Which if you, for example, have a pointer to a character array, if you declare, so then you will have a char star x, so it will be able to point to an array or to characters. Then if you do that, then you will only get the memory for the address itself. So then you have to explicitly allocate the memory if you would like to create an array to store. And but we will come back to that, how you do that in C. So, but this is one of the tricky things with C. Yes. Maybe it's good if you can move one step. Otherwise, we will have your head here. Sorry. Okay, so I started to talk about types, which is one of the other tricky areas with C. So we will go through a couple of different examples. So in this case, you declare a variable x that is of an integer type. So was this unsigned or signed? Yeah, it's signed. So all integers are signed by default. If you wanted it to be unsigned, then you have to put unsigned space int. And remember then that then the bits in the integer is interpreted in a different ways, because if it's a signed integer, then they are interpreted using the two complement method. But if it's unsigned, then it's just a position system with binary bits. Okay, so if you then put a star in front of x, that means that x is a pointer to an integer. So x is now an address, not a value. Okay, so then we have something here. X is now an array of integers, so containing 10 elements. So now you can check for elements x0 to x9. That's valid. Okay, and now we have something that is a little bit more tricky. So what is this? So you have star here, and then you have 10. Okay, so now you need to know if you should, is x here pointers to an array of integers, or is x an array of pointers to integers? So to figure this out, you need to know the precedence rule of C, which can be a little bit complicated, so sometimes it's better to put in parentheses here to explicitly denote what you mean. But in this case, it means that, so if you start with x here, so it binds tighter to the array than to the star. So x in this case is an array to pointers of integers. So it's just one of these things you need to learn and see how to interpret these things. But you could write the parenthesis here and the parenthesis here, the end of the parenthesis here, to explicitly denote that this is what you want. Okay, so if you would like to have the other way, so you would like for x to be a pointer to an array of integers, then you would put the parenthesis around the star x here. So do you see the difference now between having an array of pointers? So then we will have, the array will then have 10 elements where each element is an address to an integer. And if you have it like this, so then x is just one element, so it's an address to an array of integers. So here we represent one address, here we have 10 addresses. So the way to, if you read some code, having these stars and in different combinations, so the way to interpret it is to start with the type name and then work outwards according to the rule of precedence. So and in this case I said that this bracket notation here binds tighter to x than the star notation. So in this case, so x is then an array of pointers to integers, while if you do it in this other way, so x is now a pointer to an array of integers. Okay, so this is of course a little bit tricky before you have learned the rules. But you can always, at least when you write the code yourself, you can put in a parenthesis here to make sure you get what you want. Yeah, exactly what I said. Okay. Something else when you read code and you you will read C code because you will get the skeleton for the crazy fly that you will change, is that there can be something called type defs. So what is a type def? Yeah, it's just a way to assign a new name to a type. And the reason why you do this is because you think that the readability of your code will improve if you give the type a name that you think makes sense in the application. So for example, we had talked about characters. They are 8 bytes, 8 bits. And if you now, for some reason, would like to represent bytes, so that's 8 bits without a signed bit, so that is, it's an unsigned character. And what you can do now in C is to do a type def. So the type def, and then here you define the old type, and then you end with the new name of this. So in this case, you create a new type called byte, which is an unsigned character. So after you have done this type def, you can start to create new variables of this new type, byte, that didn't exist before. So in this case, you will have 2 variables, B1 and B2. And something that you see very often is that you do type def of structs. So remember from last time we talked about structs. Struct is like a record or sort of the attributes in the class, if you have programmed in Java, for example. So in this case, I did define a struct with a course ID, so which is an integer, and then a course name. And I put these two together in a struct, and then I use type def to define a new name for this struct type that I defined. So I call it course or course type. In this case, this was called course, right? So now, after this, you can start to create variables of this type course. So for example, I can now create a new variable called my course of type course. And then I can start to assign values to the different attributes within the struct. So for example now here, so ID. So then remember now that if I declare the variable in this way, so then there will be memory allocated for this variable on the stack. And then I can start to reference the individual fields, or fields within the struct. So in this case, my course dot ID, this is the notation you use, and then assign that to 1. Okay, so if you would so then we have given it ID, and then if you would like to continue on with giving it a name as well. So now you would like to assign some string to this name. So the way you do that is that you need to copy what's in this, what you have here, to this name field. And you do that with the string copy method. So this is just standard C. So now you have taken all this 6 characters plus one more, the 0 element, because all strings are ended by a 0 byte. So this is actually, in memory, this contains 7 elements. So the 0 byte is used by the system to know where if it prints out a string, it's used to know where the string ends. Okay, so in this case now we continue on with printing out the course ID. So you use the printf method, you give it write something here, and then you put in a placeholder here. So here we have a %d, So it means that the first argument that you have after here, which is an integer, so it will be written where you have the first %d sign here. And %d is used to denote that the bits that you have here should be interpreted as an integer, so decimal number. So you could, for example, print out multiple values, so you could have another %d, and then you send in 2 arguments, or one extra argument here. So then they will be used in the order they are specified here. But you see, you need to know what you print out. So if it should be interpreted as a decimal number or it should be interpreted as a string. So because in this case, now you print out a character array, which is a string, as I mentioned. So the way to do that is that you write %s, and then you send in the name here. Okay, so then we remember that the main method always returns an integer, so you end the program by returning 0, which is the default, that everything was fine.
Question.
Yes?
When you began here, you said when you declared your course,
Yeah?
you said it was put on the stack,
Yeah?
but you're in the main,
Yeah?
didn't it end up on its own location?
No? So the main is the first method, right? So when the system starts to execute. So when the system starts to execute, the stack is empty. So basically the first element that we will put on top of the stack here is this variable. And then when this main method is done down here, then that element will be removed from the stack. And then what will happen now is that it will go back to the operating system that started to execute this main method and continue there. Decide what to do. So I could have, if I wrote this outside here, for example, so I could have declared a global variable instead. So if I declared the variable outside the main method, then it would be a global variable, and then it would not be put on the stack. It would be allocated a specific memory, a specific slot in the static memory. Okay, good. Yes? Any other questions? Now over to something a little bit more complicated. Actually, I think I will do it in this way, because I think it's better explained with an example. So in C, you can have pointers to memory locations, but you can also have pointers to functions. And this is also something we will use in the course, because you will start to have parallel threads, and then you will specify a function where the new thread should start to execute the new task that you have. But we can see another example from a different domain here. So this is an example where you have an array of integer values, and these integer values, they should be sorted in order. So you would like to have, the first it should be 2, then 25, 56, 88, 100. Okay. So if you took an initial programming course, you probably implement some simple bubble sort or something like, yeah, some simple algorithm for sorting numbers, I suppose. But a very efficient algorithm is called quicksort. But it's not really important here. But the quicksort is an algorithm where you can sort different things. So you can sort integers, but you could sort strings as well. And what you then need to do is that you need to be able to compare the different elements that you have that you want to sort. Right? And you compare integers in one way, strings in another way, but you could also compare, for example, these courses that we had on the previous slide. for example. So, but what does it mean to, when is a course, when should it be sorted before another element? Okay, that is something you don't know beforehand. The computer can't know that, so you need to specify that. And the way to do that is that you provide a function, a compare function, that will take two elements, and then it will return an integer, so that will be using some standardized notation, so they could be able to return 0 if they are equal, and something above 0 if the first element is larger than the second one, and something negative otherwise. Okay, so now it turns out that in the standard library there is a generic quicksort implementation. So you send in the elements to be sorted. So this is an array here, and you specify the number of elements that you have, and you specify the size of each element. So this is also something you can get in C. So if you, in this case, you had integer, so each element, the number of bytes it uses is you can get by calling size of, and then you send in a type here. Okay, but the last thing here is the interesting part. So now this is the function that should be used for sorting the values. And once again, so there could be different comparison functions depending on what you wanted to sort. And in this case, we have implemented a function up here. So it takes two arguments, first and second element, to be compared. And in this case, it will take the A here and B, and then it will compare them, because integers are easy to sort. So it will just check if A, so it will be positive, you'll return a positive number if A is larger than B. It will return 0 if A is equal to B, and a negative number if B is larger than A. So this is the sort of protocol that is required by the quicksort. So you need to fulfill that. Okay, so then you can just send in these functions to quicksort, and after this the values here are sorted automatically by quicksort, and you can print them out, and then you should get the result that we just talked about. So, but the interesting part here was that in this case you sent in a function. So it was not some data type that you sent in. It was actually an address to a piece of code that would be executed to compare these values. So let's see here. So so what will be done here is that it will so when you send in values here, so remember values is an array, but what will actually be sent here is the address to the array, or the address of the first element in the array. And then remember, now we would like to change the elements here, so we can't send them in by value, we need to send in the address, right? Because otherwise this quicksort function will not be able to move them around, as we discussed last time. Because in C every argument is sent by value, so if you would like to change the content of a variable, then you need to send in the address to the variable, and then you can change the value. So A is here an address, and B as well. So and then you get the value by dereferencing A. So you take the address of A, and then you look at the value and compare that with the value of B. Okay. So, yeah, and you can do type def of functions like this that you should aim. So you could, for example, type def this comparison function and call it the comparison type, and then you can write it in this way instead. So this is something you can see as well. I don't think you need to run into that, but if you can just understand this code and what it does, it will be enough for you. Okay, so one more thing. We started to talk about dynamic memory allocation a little bit. So if we have a variable declared inside a function, we said that, okay, that variable will now be allocated on the stack. And while this function is executing, so it will be okay to reference that variable. But when it has returned, I mean, you pop all the elements from the stack, and they are no longer valid to reference. So you should, for example, never pass around the address to a variable on the stack. But let's say now we would like to, in some function, create a variable, and we would like to be able to pass around the address to that variable, and we would like the variable to be, that it should be valid to reference this variable, also when you have left the function. How would you do that? And in C, you do this by something called dynamic memory allocation. So let's say now we would like to implement the function like this. So this function should allocate an array of elements here. So a large array. So you send in the number of requested elements that you would like to have. So that's an argument. And then you return a pointer to these integers. So because each element in this is an integer. Okay, so the operating system will now provide this functionality for you. So there will be a function implemented by the operating system called malloc. And when you call malloc, you send in two arguments. You send in the number of elements that you would like to create, and then for each element, the number of bytes. So once again, if you should allocate integers, so integers, depending on the architecture, it could be 2, 4, or 8 bytes. We don't know that, but it's calculated automatically for you on your specific architecture with the size of function. Okay, so this function will now return a pointer to the integers. And now you can store that in a variable that you call big array, that you defined as integer pointers to integers, or a pointer to an integer. Okay, so when you allocate memory, you can't be sure that it will succeed. Because it might be that you have run out of memory, for example. So there is no memory available for the operating system to hand over to you. So, and if this will not succeed, it will return a specific value called null. So null means that it's not a valid address. So you can check for this. So if what you got back here is equal, so you have two equality signs equal to null, then you print out some error message, and then probably the best thing you can do here is to in this case you return null, but maybe you would like to terminate here, so you could return, and then with a failure return -1 or something like that. You could also have written here. Because if you, in the program, if you can't allocate memory, so it depends on the specific application. Can you handle it? Okay, then maybe you try to do something else, or free some memory, or do something. But in many situations, it's better to fail than to try to proceed without having allocated the memory, because then you will probably most likely you will run into other problems later on. Okay, so but if you got a valid address, meaning that this condition was not satisfied, then you can continue down here, and then you can return the big array to some other function. Then you can continue on referencing this memory. So it will never be, this will always be valid until you specifically, by calling the free function, decide to hand back the memory to the operating system. So that's the tricky part with dynamic memory. You need to explicitly allocate it, but you also need to explicitly hand it back to the operating system. And if you forget to hand it back, what will happen?
Stay there.
Yeah, it will stay there, of course. But if you continue on to allocate memory without handing it back, so eventually you will run out of memory and your computer will crash. So this is something, when you implement embedded controllers, that, I mean, they could be running for years without you restarting them. So you should be very careful with using dynamic memory. So it's better to only use statically allocated memory if that is possible. Because as soon as you start to use dynamic memory, then there is a possibility that you will forget to hand back memory, and then you can have these problems that you don't see immediately, but after some very, very long time, your memory could have been eaten up, and you have a crash. So if you have a car or something like that, this is not what you want, of course. And if you have programmed in Java, this is not something that you have been needed to think about, because in Java there is something called a garbage collector. So a garbage collector will, so you allocate new objects with the new keyword, so the new, and then you send in some class, and then you get a reference back that you can pass around. But what happens in Java is that when you can no longer reference an object, meaning that there is no variable in your program that contains the address to that memory, it will automatically be handed back to the operating system. So it will do that automatically for you in Java, but not in C. And the reason why it was, I mean, Java is a much newer language than C. And the reason it was done was because that there are many potential bugs associated with this, that you forget to do the free. Another problem is that you, for example, if you call free on some memory, and then at some other part of your program you try to reference that memory after it was freed, it will no longer be a valid reference. So then you will also have a runtime error. But what is the drawback with having a garbage collector? You know that?
That's overhead.
Yeah, it's overhead and
Takes time.
takes time, yeah. And if you're implementing now a real-time operating system, like a control algorithm, you never know when the garbage collector will run. So let's say you have a very fast control loop. You need to send out a signal every 1 millisecond or something like that. And then the garbage collector could decide to run, and then it will just stop everything else from running, take over the control, run through your program trying to figure out which memories can be referenced and which cannot, and then hand back the other things. Then you might miss your deadlines. But this is something we will talk about later when we start to talk about real-time systems. But this is another important reason why in control systems where you have deadlines that you need to meet, then you typically try to avoid using garbage collectors. Although there have been some quite good progress in having real-time garbage collectors as well. So there are extensions for that in Java as well. So these are the potential problems. We talked about the memory leak, and that you have garbage collector, or there is another strategy called reference counting, which is used in Python and also in C++. So basically, to each object you will keep a counter that states how many different variables are referencing this specific object, and when it goes down to 0, it will just be handed back to the operating system. And there are some advantages with that. Basically, that you don't need to rely on a garbage collector. On the other hand, you can have a circular reference of objects that they reference each other, and then it will not be able to figure out that it's not possible to reference it from the main program, but you just have some chain of objects in the memory that can't be referenced from the main object, but they always all have a counter that is larger than 0. We talked about this, that if you have freed your memory, you have to be certain that you will not try to use it again. And the problem with dynamic memory is that you can't rely on the compiler to help you to make sure that your program is correct. You have to so if there are problems, they will show up while you run your program. So some common errors. So always check for null if you allocate an object like that. So you know that it was. So if it was null, that means that there was a problem, and then you could print out some error message, and I think the best way is just to exit in most cases, if you can't deal with it gracefully. Another thing that you should know about is that if you have called malloc, then you will just get a bunch of memory, but you don't know what bits are in that memory. So a good practice could be to start to set all the elements to 0. So that is done with a memset function. So you send in the pointer and then the start, the value you should set it to, and then the number of bytes that you should set. You can also copy memory from one, between two different objects that are dynamically allocated, and then there is a memmove function for that. And then, as we said, when you're done, you know that the program will no longer reference a certain object, then you hand it back to the operating system by calling free, and then you send in s, where s was the variable that you got back from your malloc function. And you can set it to null afterwards, so you're really sure that you will never use it again. And then the final last slide, which has to do with the preprocessor. So we started to talk about C, that the first phase is to go through the preprocessor. And in the C preprocessor, so everything that is started with the hash sign is commands for the preprocessor. So in this case, you have a define macro here, so it will say that in your program you can then write fudge factor, and then the preprocessor, every time it will see this fudge factor, it will replace it with 45.6. So you can do this for floats, integers, strings, like that. And you can also do arithmetics with constants, for example. You can have time val could be something else multiplied by something else that is defined by the preprocessor before. So if you start to read code and you start to read FreeRTOS, you will see a lot of these defines here. Okay, so that was all about C. So during the break I got a question. I start over. So I got a question during the break about this example here and the compare function. So first of all, I would like to clarify that the compare function can compare. It will always look like this, no matter if you compare integers or strings or courses or whatever it might be. So that's why you know that you will send in two elements to be compared, but you don't know what they will look like. So in C, if you don't know what they will look like, you will use this void type. So it can denote anything. And what you actually send in is the address to some type that you don't know what it looks like. So, but in this case, we are now implement the function to compare integers, right? So the first thing that happens here is that A, which is now an address to an integer, so and that is sent to, so the quick sort, now we don't have the implementation of that, but what it will do is that it will send in the address to two integers and then have this function comparing them. So the first thing we do is that we do a typecast here, meaning that we now say that in this case we know that A is an integer or a pointer to an integer, right? Because we have written this, and if we have set up the system correctly, we know that the quicksort algorithm will only send in pointers to integers to the compare function. Okay, so now we know that, and then we can look at this address that is pointing to an integer and get the integer itself. So that's what we do with the star, because then this is an address and now we get the value at that address. So now so after we have done the last star here, we now have two integers to compare. So, and this function is implemented by just taking the difference between those. So this is something, so this casting is something you can see quite often. So if you have a variable name and then something in front of it in parentheses, that's a typecast. So you change the type, or you don't actually change the type physically of the object, but from the compiler's point of view, the compiler will now know that, okay, this is an integer, or pointer to an integer that you have here. So then it can do its type checking during compilation, which will be helpful in finding bugs. Okay, any other questions regarding this example? So Now we didn't look at the implementation of this function that got where we sent in the comparison function, but we will look at how to reference this or call this function on Monday, I believe, when we start to talk about the implementation of a parallel task in FreeRTOS, because then we will have problems like this. Okay, good. So then at least you have got some quick introduction to C. And now we will switch over to an introduction to real-time systems.
You don't see the screen?
Yep. So, because as control engineers that you are, you will typically implement real-time systems. So, and we will come back to that. What do we actually mean by a real-time system? But we can think about control systems. So, we read something, sensors, we do some calculations, and we generate some outputs. And it's not only important that we calculate the right control signal, it's also important when we calculate the right control signal. So this is a difference from normal algorithms that you have done before. So for example, if you have the sorting algorithm, then it's important that you sort the items in the array correctly. But you don't, the timing is not important. But for real-time systems, it is. Yeah, so we will talk about response times, soft, hard, and firm real-time systems, event, and what do we mean by deterministic system. And then after that, we will switch over to real-time operating systems, which is a special type of operating systems that are used to implement embedded or real-time systems. And they are typically simpler than normal operating systems, but on the other hand, they can give better guarantees on the timing, for example. So we will talk about processes and threads, schedulers, and context switches. Yeah, so this is the system architecture for the Crazyflie. So, and it's important here that we have some sensors, the IMU, for example. We have the computational unit, the main processor here, and it is controlling something, for example, the different motors. So this is an example of an embedded system, and you have you need to have some bound, for example, on the control signals. So if you're not computing the control signal often enough, the Crazyflie will fall down, of course. Yeah, and what is important is that on this Crazyflie there is a real-time operating system called FreeRTOS that is used that you can call to create parallel threads or parallel tasks. So you can have parallel control tasks that are executing, and then the real-time operating system decides which, since only one task can execute at a time, the real-time operating system will decide when to switch between the different tasks. And it's implemented in C, and you will actually, everything is open source and it's free. You can go in, you can actually read the source code of FreeRTOS. And I think it's basically 5 files that you need to read to see how it's working. So it's not that complicated actually to write your own operating system to do these things. But nowadays there are many of them. It's quite hard. It's quite easy to get something that would work roughly approximately, but to get it right in every specific situation, it's a lot of work, and there are a number of different free real-time operating systems and commercial for that matter as well, but free RTOS is a very popular one. Yeah, so we talked about real-time control systems. So you have inputs in form of the different sensors, cameras, etc. You have the control algorithm, and then you control something. So the crazy flight was the IMU, then you have the control unit, and then you control the motors. Yeah. So something that we intuitively know now is that there will be, after you have read a sensor, until you compute a control signal. That is important, right? So let's say we are controlling an inverted pendulum. If that time is too long, when it will fall down before you start to change the control signal, right? So this is, of course, especially if you have unstable dynamics in your plant, then things can go crazy before if you don't control it. So that's why this response time is so important. And it's basically the time between the inputs to a system are known, and the time you will have changed the outputs. And what does this mean, really? So for the type of control systems that we have defined, the bounds on the response times that you have, or that you must fulfill, depends on the specific type of system that you're controlling, right? So a common misinterpretation with real-time systems is that you need to have very fast response times, but that's not the idea. But you need to have known response times. That's the big thing. So because when you discretize your controller, you have done that under the assumption that you will have a certain sample time, right? So if you will not be able to meet that sample time, it means that the gains you have used in your controller design, they will be completely wrong, and scary things might happen, really. So with the real-time system, we mean here that it's a computer system that must satisfy a bounded response time constraints, and if it doesn't fulfill these constraints, it might fail. For a real-time system, it does not only depend on the logical correctness, meaning, for example, that we sorted an array correctly, but also that we did it on time, that we have set up. And it might be very tight to do this, or it can be quite relaxed, and that depends on the application, for example. So if you have chemical processes, they are typically quite slow, so they are not very sensitive to, or you don't need to compute the control signals very fast. But if you do, for example, engine control or something like that, then you have very tight bounds on the when you need to generate your control signals. So you have bounds on when you need to generate the control signals, but we often divide into different type of real-time systems then. So with the soft real-time system, we mean a system where the performance will degrade if you not meet the response times. So it will still work correctly, but it will control your system in a little bit worse way than other ways. And the opposite is hard real-time systems. So with a hard real-time system, you mean a system where if you don't meet the deadline, really bad things will happen. So for example, catastrophic system failure. So you can, think about system, you're going to land on Mars, for example. You need to do things in a certain time, otherwise the whole system will be completely useless. But when we start to think about control systems, so in most cases, they are what we call firm. And with firm we mean something that is a little bit between soft and hard real time. We still have designed the controller for a certain sample time. We would like to meet that sample time, but usually the system will not fail completely if we miss 1 or 2 deadlines when we're executing our controllers. So I would say that is the most common situation. So soft real-time system could, for example, be if we play music or video. So you have real-time, you need to compute the different frames, but what will happen is that you will just look bad if you don't meet the deadlines. But for control systems, if you have an unstable system like the JAS air fighter, for example, that need to be actively stabilized all the time, you have a hard or more likely a firm. You can, in this case, I think you can. It's okay to miss 1 or 2 deadlines, but you can't miss many of them because then the system will fail. So of course, if you have a stable plant, then it's typically, or if it's unstable, for example, like this inverted pendulum, then you typically can allow less deadlines to be missed. Okay, so this was just, the difference between soft, hard, and firm real-time systems, and that firm real-time systems is what we typically deals with. We also talk about punctuality. So and that is basically the lower and upper bound on the response times. And what typically happens is that you have variation. It varies the response time for the different sampling times of the controller, for example. And one reason why the response time can vary is because if you have several different control tasks executing in parallel, and they have different priorities, so you have a high priority process and a low priority process. So let's say if you now look at the response time for the low priority process, so you will have one response time if the high priority process does not want to execute. But if the high priority process decides to execute, so it will preempt the low priority process, so throw it out of the main CPU, and it will start to execute, and then when it's done, the low priority process can continue. So of course then the time from reading the sensors to output in the control system will be longer if the high priority process has run in between. So this is something that complicates the analysis of the behavior of control systems. And the word that is good to know is the word jitter. which is this interval between the lower bound and the upper bound here. So it describes the variation in response time. Yeah, so and just an example here. So if you have an elevator, so you can have the door and they will close, right? So and then you have sensors that you detect if there is a person between the doors, right? Because then they should open up again. So this is a sort of real-time system, because if you don't detect if you don't act fast enough, then the person will be crashed, or it might hurt at least. So what can you then do? So if you would like to do a response time analysis, to set up or to do an analysis of this application, so then you have to look into the different components that the system consists of. So you have the sensor, you have the computer hardware, you have the software. This is the real-time operating system, and then you have the application software, your control task, and then you have the physical door drives, the motors controlling the doors. And what you can then do is that you go in and then you identify what is the minimum response time and maximum response time for each individual component, and then you can compute the sort of combined response time. So you will get the lower and the largest value. So if we look at the numbers here, we see something that is quite typical, and that is that the hardware and the software, here we talk about microseconds typically. The sensors are a little bit slower, but the slowest part is more or less always the actuators. So keep that in mind, that do not only consider your control task, but also the environment here that puts the bounds. You see in this case, if you look at the numbers, so you had 300 milliseconds on the door drive, and all the other, in total, they added up to 5 milliseconds.
Actually, that 5 milliseconds is coming from the sensor.
Yeah. So these are just thousands of milliseconds. Yeah. So it's basically the sensor. So in this case, it's completely dominated by the first actuator, then the sensor, and then everything that's in the software or hardware is basically negligible. Yeah. Okay. We also took a course on discrete event systems. And discrete event systems, or what do we mean by an event? So, and in this case, with an event, will mean something that causes the program counter to change in a non-sequential way. So remember, the program counter is the address of which instruction to execute next in your computer program. And can we think about an event in a control system? So one example, for example, is that the user can press a button, right? And when the user presses a button, what typically happens is that there will be you have two ways basically. You can periodically go out and read the state of the button. Or you can have the button hooked up to an interrupt inside the processor. So with an interrupt, it means that with an interrupt you have defined a certain piece of code. You can connect that to inputs to your microcontroller. So as soon as some input goes high, then the computer will stop executing what it's doing right now, switch over to some predefined code, and execute that instead. So this is something you would like to do typically for an emergency button, right? So no matter what you're doing, if a user presses the emergency button, then you should switch over, execute some other code, and shut down the system in a nice way. So that's an event. And events could also be connected to, for example, timers. It's another very common use of events. So if in a control system, so we have periodic events because we would like the control algorithms to be executed periodically, right? And the way we do that is that we connect an interrupt to a timer inside the processor. So we set up, okay, call me, execute this piece of code, implementing the control algorithm every 5 milliseconds. So then the control code will be associated to the interrupt. And then we can think about that as a periodic event. And this connects very well to the release time. So if we now have a control task, and the control task should execute periodically. So that means at the start of the period, then that task is released. So when it's released, it means that it's now ready to execute. But it might not be able to, since there might be other tasks as well, it might not get access to the processor because there might be some other task that has higher priority that is currently executing. So it just means that the task is ready to execute. So it wants to execute. So it's in queue, so to speak, for execution. So then it will, at some point, it will be allowed to execute on the processor, and then when it's done, what will it do then? Yeah, it will wait. It will go into blocked mode. So then it will wait for the next period to start. So then it's not ready to execute any longer. So it will switch between ready to execute and waiting for the next period to start. Right? And the first time when it's ready to execute, the beginning of the period, that's called the release time. Yeah, so events can be synchronous or asynchronous. Synchronous events occur at predictable times, and asynchronous events occur at unpredictable times. For example, the button that I talked about. But what we typically talk about is this periodic, aperiodic, and sporadic events. So, for example, the control task, that is a typical periodic event. And then we have events that are aperiodic, so they could just happen from time to time. But they are still sort of happening regularly. And then sporadic events are just those that happen very infrequently. The system will break down or something like that. Yes.
Can we turn off this light? The lights over there.
Oh yeah, sure. Let's see. Oh, it's better? Yep. When you took the discrete event systems, you learned about discrete and deterministic and non-deterministic systems. And we will use a very similar definition here. So a system is deterministic if we know which state we started in and we know the inputs to the system, then we will know which state the system is in. Right? So, yeah. System is deterministic if for each possible state and each set of inputs, a unique set of outputs, and the next state of the system can be determined. And this is something, when we have control systems, we would like them to be deterministic. And what is the reason for that? Yeah, the reason for that is that the control systems, they are critical for the correct behavior of our system. And systems that sort of can behave in one way and then suddenly in a different way will be very hard to analyze. So we would like them to always have the same behavior. And this is, so actually, we will come back to that, but on the Crazy Fly, when you have a normal real-time operating system, that system will not be perfectly deterministic, at least not in the sense that when you analyze the application, you will have all the, even if you know all the control tasks that you have, how they are executed will be decided by the scheduler. And if you don't know how the scheduler will behave, you don't actually know. So basically the interleaving between the different control tasks can be different from time to time. So that means that you could have a system that works very well for a very long period, but then suddenly the scheduler decides to do something unusual and schedule the different control tasks in a different order, and then boom, something happens. And things doesn't work very well any longer. So a way to get more deterministic system is also to have the scheduler to be deterministic. And there is something called synchronous programming languages that will help you with that. For example, SRL. So if you go into space applications and control software for aircrafts, they are typically not implemented using C, which is, if you go in the automotive industry, C is the sort of standard language. But if you have really critical software, then you start to use other languages that have this property, that they are more deterministic. Basically, the scheduler will be a state machine that will always behave in the same way. Of course, to get that, you have to give up something else. And one thing you give up is the ability to have to start tasks dynamically. So you need to know all the tasks beforehand, and then you decide on when they should execute. But it's an important property that we would like to have. We get closer to having deterministic systems when we have real-time operating systems than if we have just standardized desktop operating systems like Windows and Mac OS X. Okay, so this brings us to operating system. So what is an operating system? So yeah, so basically an operating system provides an environment for executing different programs. And even without thinking about it, on our desktop computer, we can have parallel tasks running, right? So we have the web browser, we can have a word processor, and the PowerPoint presentations, all started up at the same time. And it's an operating system that makes this possible. And so it provides the abstraction then for starting these multiple programs, and it's responsible for the scheduling. So meaning that throwing in and out different threads or tasks from the processor. So only one task at a time can execute, and then the operating system will be in charge of that. The operating system is also in charge of interfacing with the hardware. So here we have the mouse and the screen, but in the applications we have in mind, it's the IMU and the motors instead. And on the desktop operating system, we have, of course, we have a big disk and a file system. So this is a thing that we don't always have on our real-time operating systems. And then today you also have some form of communication, and for desktop computers it's TCP/IP, which is the protocol that is used for the on internet. So for a general operating system, you have you need to deal with the file system, etc. But for embedded control system, the main task is to schedule the different concurrently executing control tasks in such a way that they will meet their deadlines that you have set up. So what is different when it comes to real-time operating system is that you have tasks in the same way, but now you have hard or firm real-time constraints, which you typically don't have on your desktop computer. And another difference is that while in a desktop computer you would like it to behave nice, so if I move the mouse, the cursor should move, but it has, so for desktop computer the average response time is much more important, but for control systems it's the worst case response time that matters most, because the system might fail if the worst case is too bad. And if you go to, in the automotive industry, you go to the SSY190, I probably mentioned that you have about 150 computers, and they are hooked up to different networks. So you have one network for the critical control tasks like engine control. There is another network for the entertainment system, for example, so you don't put that same, so you have different needs for the different networks, and you don't want to put the traffic on the same network. So that's why you have a couple of different networks on a car. And if you go to a truck, for example, you will have even more networks. So they are distributed. So you have this 150 computers, and they need to talk with each other, and they're using this. And they are safety critical. And another aspect is that they typically run over very, very long periods of times, which means that, for example, if you on a desktop computer, if you have a memory leak, I mean, you can restart your computer after some time, but or you often do, right? But if you have sending a satellite or writing code for a satellite, you don't want to restart it really. So it can be running for years. And as I mentioned, we will use FreeRTOS in this course. VxWorks and QNX are two commercial real-time operating systems. So they basically provide the same functionality as FreeRTOS, but you have commercial support. So VxWorks, for example, I think is used in the robotic controllers from ABB. At least it was like that a couple of years ago. But there is a strong trend today that you're moving away from these commercial operating systems to open source systems. So FreeRTOS is a very simple operating system, but Linux, possibly with some real-time extensions. RT Linux is one. There is also another version of Linux that will give you sort of soft real-time guarantees. But if you would like, it's still a big kernel in Linux. But the advantage is, of course, that you get everything for free, including the communication, all the TCP/IP, all software connected to that. You have the file system, many different file systems you can use, and so on. So this is, of course, a big time saver if you're going to build large complex systems. So there is also a specific version of Windows that called Windows Embedded that you can use for real-time purposes. But Linux is now gaining a lot of attention. So I have talked about processors, threads, and tasks. So I will try to be a little bit more specific what I actually mean with these different words. So if we now take a computer like that, we have some physical memory. So I think on this computer I have 16 gigabytes of memory. And then I will have different processes. So, and different processes, they are living in sort of their own view of the memory. So you can't access the memory from process 1 in process 2 and vice versa. They are separated. And the reason why you do this is that if you make a mistake in process 1, it should never be able to bring down what you do in process 2. Right? So they are isolated from each other. But when you have different threads, which is actually what we will use in FreeRTOS, then you can have, for example, variables that you can access from both of the threads. So they are living in the same memory. So yeah, variables. If you change the variable on some variable in thread 1, you can read the new value from thread 2. But each thread will have its own stack. It will have its own view of the register, and it will have its own process counter. Program counter. So the program counter was the address to the next instruction to execute. So they will all, each thread will have their own point of execution in the program and its own stack. And then basically you can, when you start, you can decide if you would like to have a new process or a new thread, and the real-time operating system will give you that, and then the real-time operating system have something called the scheduler, which is now responsible for all the different processes and threads that are started to decide, okay, which one to run. And of course, we talked about when the release time of a task. So when a task is released, it's put in the ready queue. So the real-time operating system will maintain a queue of threads that are ready to execute. And in a real-time operating system, each thread will have its own priority. So it will be an integer. And this queue is then sorted on this priority. So it has a very simple principle. It will always take the process with the highest priority to execute first. So, and it will look in this queue of processes that are ready to execute. So, and then you can have 1 or 2 processors. I mean, some years back, all processors, they only had 1 computational core. But I think I have 4 different cores on that laptop. And I think if you buy a new Raspberry Pi, you will get 4 cores as well. So then actually you can have more than 1 thread or process executing at a time. So in the future, when we talk here, we will mainly talk about threads, but I might use both threads and processes and task. And with a task, I mean that's a generic term for threads or processes. So in most cases, it's not important if they share memory or not. So then I will try to use the task, the word task. Yeah. Okay. So yeah. So with that, we will be done with this, and then we will switch over to the implementation next week of these real-time operating systems and what services they provide. Okay, thank you.